Hello everyone. I'm very happy today to introduce my work, Entropy Guided Pruning algorithm for reducing the size of deep neural network. I'm working with Victor, Van-Tam, and Enzo. Okay, Victor will be the next presenter. Maybe later he will say, I'm not working with you. But please trust me, I'm really working with him. We come from Télécom, and today I'm going to introduce my work from those four aspects. First, introduction. Is there anyone here who has been to Paris? Nobody? Yeah. Okay, congratulations. There are someone has been to Paris. Yes, this is a photo that I have taken for Paris. I think Paris is very beautiful, so I have taken a lot of photos by my phone. And now I think there are maybe thousands of photos in my phone. However, even though my phone can contain thousands of photos, it cannot contain everything. For example, ChatGPT, which is very famous recently. The model size for ChatGPT is around 100 gigabytes, which means the model size of ChatGPT 3 equivalent to 1 million photos. Operating such a big model costs a lot of time and energy. A good technology for me should always function more and cost less. It seems nowadays AI can help us to do more and more things. So the question is, how can it cost less? My work is here to help. I'm trying to reduce the model size of deep neural network in AI. So this is a figure for deep neural network, which we often used. And in deep neural network, we typically use ReLU activation function. You can see from the figures. There are two parts for ReLU activation function, the nonlinear part and the linear part. For the nonlinear part, no matter what is the input, it outputs 0. And for linear part, no matter what is the input, the output is the same. So I know here we have master students from Paris-Saclay and IBE. I used to be a master student in both IB Paris and Paris-Saclay. So I know how hard your study is and how extraordinary you are. Yeah. Now, let's take an image. What if I am an M1 student here, and I always get 0 score? No matter what the teacher told me, I cannot write anything in the exam. I always get 0 over 20. So what will happen? I guess I will be kicked off. My teacher will tell me, okay, Zhu, you should stop your study. Your name will be removed from the class list. Let's take another image. What if I can always output the same as the input, which means no matter what the teacher teaches me, I can teach others for the same. I can always get 20 over 20 in the exams. In this case, what will happen? I think my teacher will tell me, okay, Drew, you do not need to stay in our class. You can go to the higher level. You can be observed by the next level. If I am an M1 student, I can go to M2. Okay, it's the same for our ReLU function in deep neural network. If a neuron always outputs 0, why it needs to stay there? This neuron can be removed. And if a neuron always uses the linear part of ReLU activation function, which means it always outputs the same as the input, this neuron can be observed by next layer by linear combination. Based on this knowledge, we developed entropy guided pruning. But first question is, what is pruning? Pruning means remove something. Like in pruning in deep neural network, we are trying to remove some weight parameters. nowadays in deep neural network, unstructured pruning is traditionally used. So what is traditional unstructured pruning? Let's make an example. Okay, today I want to remove 50% of the weight parameters inside that model. I will ask, okay, all weight parameters come here, and today I only want 50% of you stay here. So for the weights whose magnitude is under the average, you can go. I do not need you anymore. Only for the weights whose magnitude is larger than average, stay here. So this is what traditional unstructured pruning does. And we are trying to do something different. Based on the knowledge that I have just introduced for ReLU, there are two parts of ReLU activation function. For the linear part, we also call it on region, and the nonlinear part, we also call it off region. So the ReLU activation can be in two states. State 1 corresponding to on state, and state 0 corresponding to off region. We calculated the possibility for the neuron to be at the on region, P on. It's the frequency that how often does the neuron stay in the linear part. Surprisingly, the P off equivalent to 1 minus P on. Because this neuron can either stay in P on or P off. And then we used Shannon entropy to calculate the entropy for a neuron. We can say from this formula, the entropy equivalent to P on multiply log P on plus P off multiply log P off, then normalize it by the log 2 because there are two states, so we normalize it by log 2. And then the entropy can only stay the entropy can be 0 only in two cases. First case, the P on equivalent to 1, which means the neuron always stay in linear region. Another case is the P on is 0, which means the neuron always stay in the nonlinear region. So as we want to decrease the size of the model size, we want more neurons that stay always on region or off region, then we can remove it. As we want more neurons to be in the two cases, and these two cases corresponding to entropy 0. So our question can be transferred. Previously, we want more neurons that can be pruned, can stay in always on region or off region. Now, our question transfers to we want more neurons as the entropy 0. So in order to reduce the depth of deep neural network by removing 0 entropy layers, we used entropy guided pruning. Attention, here, we are not only want to remove some neurons, we want to remove some whole layers. If a layer only contains the neuron in always on region or always off region, this total neuron can be removed. So here is our workflow. After we import our model, we evaluate it, and then we calculate its entropy. We remove the neurons whose entropy is 0. And if a layer only contains the neuron with entropy 0, we remove the whole layer. So we get a sparse model. And then we implement the entropy guided pruning on the model. We prune more parameters on the layer who has the lower entropy, which means for the lower entropy layer, this layer can be easily achieve the entropy 0. And then after pruning the parameters, we retrain our model to retrieve the performance, then we evaluate it to say, okay, if this model still performs well, if it does, okay, we continue our loop, we continue calculate the entropy, we continue remove the neuron whose entropy is 0, and we continue pruning the layers whose entropy is lower, is very likely to achieve 0. Here are some results for our entropy-guided pruning, and compare it with traditional unstructured pruning. We can see from this table the gray row is the results for our entropy-guided pruning, and for the row without gray, it's the traditional unstructured pruning. We can see from the table, in most cases, our entropy-guided pruning has the comparable results with the traditional unstructured pruning, and even in some cases, our entropy-guided pruning could have a better performance. So the performance is good, which means the accuracy is still very high. So can we really remove some layers? Let's see in the next slide. Yes, we can. Here are some histograms of our results. In the histogram, the X3 is the number of layers, and the Y-axis is the number of neurons. For the orange part is the number of neurons who always stay in the nonlinear part, and for the red part is the neurons who always stay in the linear region. So for the red and orange, those neurons, we can totally remove it. This is the vanilla trained model without any pruning. We can see from the figure, there is no neuron that we can simply remove it. And with traditional unstructured pruning, we get the figure in the middle. There are some neurons that we can remove it, but there are no layers that we can wholly remove. And however, with our entropy-guided pruning, at the same sparsity 98%, we get 3 layers that we can totally remove it, which means we can largely reduce the depth of deep neural network. Okay, finally comes to the conclusion. So in our work, we have investigated the impact of unstructured pruning on the entropy of activation in deep neural network, and we have proved that our entropy-guided pruning can drive more neurons to stay in either on or off region. And we have proved that unstructured pruning can, in some cases, can really reduce the depth of deep neural network. In future, we will try to apply our work to other data sets, other models, and even in other activation functions. And we will try to design a regularization function to push the design a regularization function and during the training to push more layers as the lower entropy, even the entropy with 0. And thanks to this work, we can reduce the model size, and with the smaller model size, we can save time, save money, and energy. Okay, thank you. And do you have any questions?
For your presentation, and let us know who has questions. Okay, you.
Thanks you for your presentation. I have a quick question about can your proposal apply to all the architectures, like transformer-based architectures or CNNs as well?
Okay, this is a very good question, and this is what we are going to explore. And by now, we are aimed at the because not all architectures has such a function, like for such an activation function. So what we have done is based on the review activation function. So for the most models with review activation function, we can implement this. But however, there are some models that if we remove the whole layer, because there are some, they are not simply connected layer by layer. There are some reschedule connections, so this question can be more complex for those kind of models.
Yeah, I have like, do you think that the Pruning parameters, the way they are redundant, or you got the chance that in your data set, like you had a full data set that you didn't need that parameters, and in the case you will get the auto distribution data set, your model will not have the good performance. Because if I'm not mistaken, one of the main problems of the pruning is that it will not work on the auto distribution data set. Like whenever you will get a new image or the new samples after training your model, are you sure that your model will work as good on the new samples as on your data set?
Okay, this is a very high-level question. Why I say this is a high-level question? Because there are several papers trying to explain this question. So let me give you a very quick explain. So firstly, for pruning, so we can say this this model is kind of redundant. Yes, it is. However, why pruning works is only with redundant parameters it can be trained to that well. So we have also done some, as we can totally remove some layers from the experiments. We have done the experiments, we have tested that. What if we start with, let's say, just as you mentioned, it's redundant, so we only keep the layers, and after training, we start from the very beginning. So it cannot perform well. So we still need those parameters that work together to get it trained very well, and then we can remove the useless parameters.
Okay.
There is one more question.
Yes, I was just curious to know how do you go about the pruning? Is it like an exhaustive search of like the activation of one ReLU? For example, like if you take in the first layer, the ReLU function there, you try to trace the path to the output, or how do you go about knowing that, okay, maybe if the activation of a ReLU doesn't work, and is it kind of like computationally expensive to do the pruning or lightweight as well?
Okay, I don't know if I understand your question well, but like for you, do you mean that how can we know a neuron's output in operating or linear region?
No, that we can know from the function, but the question is, for example, how do you go about selecting, like, okay, this ReLU is in the redundant because you do an exhaustive search of the activation of this neuron throughout the entire network, and is it expensive to do, or is just a lightweight approach?
Okay, we just get we take the record for the output of the ReLU activation function during the training process. So we can say, okay, if it always on the linear region or at the non-linear region, okay, we remove the whole neuron, not the single activation function. Because each ReLU activation function is attached after a neuron.
Okay, and just to add to Ali's question, I think it would be better to assess this method based on like a robust data set, because the activation of the neuron might not be working on your validation set, but on another, it might have an impact on the performance. So I think that would be a good idea to see if you can have a robust data set, or like for any task, the benchmark, and you try to use such a data set, would be a good thing to know whether pruning is actually generalizable or not.
Okay, thank you for your suggestion.
Thank you once again for your presentation.